In this video, we'll be continuing Chapter 7, Covalent Bonding. Lesson 3, Molecular Structures. Here's your essential questions for Lesson 3. So, what are the basic steps to draw Lewis structures? Why does resonance occur? And which molecules are exceptions to the octet rule? Topics and sections of structural formulas, resonance structures, and exceptions to the octet rule. Here's your vocabulary. So structural formula, that's going to be a molecular model that uses symbols and bonds to show the relative positions of atoms. The structural formula can be predicted by drawing the Lewis structure. Resonance occurs when a molecule can have more than one Lewis structure. A coordinate covalent bond occurs when one atom donates 2 electrons to form a covalent bond. Structural formulas. So when we study about covalent compounds, we use models to represent the molecule. So there's several different models that we can use. For example, the molecular formula, that's just going to show the element symbol. So right here, so we have P for phosphorus, H for hydrogen. And it's going to have numerical subscripts. So these numbers, these little numbers at the bottom, these are called numerical subscripts, and that's going to show you how many of each atom we're going to have for that particular molecule. We have 2 different models that use spheres in different colors to represent molecules. The first one, the ball and stick model, uses spheres and rods along with different colors to show different elements. The space filling model shows the spheres, but they lack the rods. And remember, the different colors are used for different elements. So for example, the purple sphere you see is going to represent phosphorus, and the blue spheres that you see are going to represent hydrogen. One of the most useful molecular structures is going to be the structural formula. So for the structural formula, you're going to have the element symbol, and it's going to be connected by these bonds. It uses letter symbols to represent the elements. For example, this P represents phosphorus, and it also shows lines to represent the bonds. Remember, you can predict the structural formula of any molecule by drawing the Lewis structure. So here's a Lewis structure. So here's phosphorus in the center, and it's connected by these lines, and these lines are going to be the bonds. This pair of electrons up here are called a lone pair. Lewis structures. Although it's fairly easy to draw Lewis structures, it's still a good idea to follow a regular procedure to make sure you're consistent. Lewis structures procedure. Step 1, we're going to count all of the valence electrons. Step 2, we'll write out the symbols for the atoms, and then we'll connect them with single bonds. And when you write the symbols for the atoms, you want to try to determine what the central atom is, and usually that's going to be the element where there's only one. Step 3, complete the octets around all of the atoms bonded to the central atom. Step 4, put all of the remaining electrons on the central atom. Step 5, if there's not enough electrons to form an octet, try to do multiple bonds. So you can turn some of the lone pairs into double or triple bonds to give every atom an octet. Alright, so let's start out with an example for oxygen. So remember the first step, so we're going to count all of our valence electrons. So we have oxygen, and we are going to have 2 of them. So if you look at a periodic table, oxygen is going to have 6 valence electrons since it's in group 16. So we'll have O2. So each one of those is going to have 6 valence electrons. And remember, we have 2 oxygens, so we're going to multiply by 2. So we'll have 12 valence electrons. So let's draw our oxygens. So we have oxygen and oxygen. Now remember our second step, we're going to draw our symbols and we're going to connect them with a single line. So this represents a single covalent bond, and when we have a covalent bond, we're going to have 2 electrons. So this represents 2 electrons. So we've already used 2 of these, so now we have 10 left to work with. So let's try to draw those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like we didn't get an octet on this side. So when we don't have an octet, we can try to put double or triple bonds in. So let's try it again. So we have oxygen and oxygen. Let's try a double bond. So we have 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we used all of our 12 valence electrons that we needed. And each one has an octet, so 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So now this is our Lewis structure for oxygen. Alright, now let's try CH4. So let's go back to our periodic table. So if we see carbon, that's going to have 4 valence electrons since it's in group 14. Hydrogen is going to have 1 valence electron since it's in group 1. Alright, so back over here. So let's count our valence electrons. Carbon is going to have 4 valence electrons, and it's only going to be 1 atom. So 4 times 1 is 4. Alright, what about hydrogen? So hydrogen is going to have 1 valence electron, and how many of them do we have? So we have 4. So that's going to equal 4 valence electrons. So when we add these together, we'll have 8 valence electrons to share. So 8 valence electrons. So 4 from the carbon and 4 from 4 hydrogens. So let's try to draw these out. So we have carbon in the center, and then we'll have hydrogens. 1, 2, 3, 4. So carbon's going to have 1 valence electron, 2, 3, 4. Then hydrogen is going to have 1, 1, 1, and 1. Now remember, hydrogen only needs 2 valence electrons to complete their shell. Carbon will need 8, so this carbon is going to have 2, 4, 6, 8. This hydrogen is going to have its 2, this hydrogen is going to have its 2, this hydrogen is going to have 2, this hydrogen is going to have its 2. So if you want to draw your Lewis structure, so we'll draw carbon in the center, hydrogen, 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 and then we'll draw our lines. So bond, 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 bond. Remember, each one of these lines represents 2 electrons, so 2, 4, 6, 8. And remember, hydrogen only needs 2, so that has its 2. Hydrogen only needs 2, only needs 2, only needs 2. Alright, in this example, let's try to do CO2. So if you look at a periodic table, carbon is going to be in group 14, so it'll have 4 valence electrons. Oxygen is in group 16, so it'll have 6 valence electrons. So let's count our valence electrons. So for carbon, carbon only has 4 valence electrons, and it'll have only 1 carbon atom. So that'll be 4. Oxygen has 6 valence electrons, and remember we have 2 atoms of oxygen, so we'll multiply by 2. So now we're left with 12. Alright, so if we add those together, so 12 plus 4 is going to be 16 valence electrons that we can use. Alright, so let's try to find our central atom. So remember, our central atom's usually going to be the one that there's only a singular one of. So let's have carbon in the center, and then we'll have oxygens on the end. Now let's draw our bonds. So we'll start off with a single bond connecting the carbons and the oxygens. Alright, so now that we used 4 electrons, remember each one of these lines means 2, so that's 2, that's 4. So 16 minus 4, that's going to be 12, so we have 12 left. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so let's try to count to see if we have our octets. So this oxygen, we have 2, 4, 6, 8. That's good. 2, 4, 6, 8. This oxygen's also good. What about this carbon? We only have 2, 4. So this carbon is missing an octet. So let's go to our next step. If we don't have enough electrons for a central atom, try to put in double or triple bonds. So let's just try to make a double bond on this left-hand side. So let's get rid of these 2 electrons and use them to make a bond over here. So let's go back and count these electrons. So 2, 4, 6, 8, 2, 4, 6, 8. But for the carbon, we only have 2, 4, and 6. So we're also going to need another double bond from this oxygen. So let's get rid of these 2 electrons on this side. Let's make another bond here. So how about now? So 2, 4, 6, 8. 2, 4, 6, 8. And this carbon now has 2, 4, 6, 8. So all of our atoms have their octets. Lewis structure for polyatomic ions. To find the total number of electrons available for bonding in a polyatomic ion, first, try to find the number of electrons in the atoms present in the ion. Then, if the ion's negative, add that charge. Or, if the ion's positive, subtract the charge. So, when you have a negatively charged ion, it's going to have more electrons. When it's positively charged, it's going to have less electrons. Alright, so let's try the phosphite ion. So PO3, 3 minus. Alright, so remember with polyatomic ions, it's going to be a little different. So to find the number of available electrons, what we're going to do is do the same thing that we did before. So let's go back to our periodic table. So we have phosphorus, that's in group 15, so it's going to have 5 valence electrons. Oxygen is in group 16, so it'll have 6 valence electrons. So now let's try to find the number of available electrons. So phosphorus, we said, it's going to have 5 valence electrons, and since it's only 1, it'll multiply it by 1. So 5 times 1 is 5. So now what about oxygen? So we have O3, so oxygen is going to have 6 valence electrons, and since we have 3 of them, we'll multiply it by 3. So 6 times 3 is 18. Now remember, for an ion, if the charge is negative, we're going to add the charge. If it's positive, we'll subtract the charge. So since this is negative, we have 3 negative. So that's going to turn into 3 electrons that we're going to add on. Alright, so 5 plus 18 plus 3, that'll give us 26 valence electrons. So we have 26 valence electrons we have to work with. So now let's try to find that central atom, and we'll try to figure out the skeleton of this ion. So we have phosphorus, that's going to be in the center, and then we have oxygens attached to it. Now our next step is to make our bonds. So remember, each one of these bonds means 2 electrons. So we have 2, 4, 6 electrons that we used so far. So 26 minus 6 is going to be 20. So that's how much we have left. So let's start filling them in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now remember, once everyone has their octet, we'll start adding electrons onto the central atom. So we have 18, 19, 20. So this is the Lewis structure for phosphite. And don't forget, since we have an ion charge, we're going to put brackets around it, and we'll have a 3 minus charge. So here's an example of an ammonium ion. Ammonium is going to be NH4+. If we go back to our periodic table, so nitrogen is going to be in group 15, so that has 5 valence electrons. Hydrogen is in group 1, so that has 1 valence electron. So let's count our electrons. So we have nitrogen, so that has 5 valence electrons, and since we only have 1 of them, we're going to multiply it by 1, so we have 5 valence electrons. Now for the hydrogen, that's going to have 1 valence electron, but how many do we have? So we have 4, so that's going to be 4, and then we have a 1 plus charge, so that 1 plus charge is going to be positive. So remember, if we have a positive ion charge, what are we going to do? So we're going to subtract the number of electrons. So we're going to have 1 minus. So 5 plus 4 minus 1, that's going to be 8 valence electrons. Alright, so now we can start drawing this out. So we have nitrogen in the center, since there's only 1 of them. So you know that's your central atom. Now we'll surround it by hydrogen, 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 hydrogen. So how many valence electrons does hydrogen have? So it has 1, hydrogen has 1, 1, 1. And then nitrogen, how many valence electrons does that have? So we have 1, 2, 3, 4. And remember, the positive charge means that we lost an electron. So nitrogen only has 4. So nitrogen is going to have its 2, 4, 6, 8. Hydrogen is going to have its duet, so it only needs 2. So the way we write this, we're going to write it as N surrounded by hydrogen atoms. So don't forget, since it's a polyatomic ion, we're going to surround it in brackets, and it's going to have a positive charge. Here's an example with hypochlorite, so that's ClO-. So if we go back to our periodic table, chlorine is going to have 7 valence electrons since it's in group 17. Oxygen is going to have 6 valence electrons since it's in group 16. So now let's find the number of available electrons. So first we have chlorine. So that's going to have 7 valence electrons. And how many do we have? So we only have 1, so we're multiplying it by 1. So we have 7 valence electrons from the chlorine. Alright, so now with the oxygen, so we have 6 valence electrons with the oxygen, and we only have 1, so we're multiplying it by 1, 6. Now, since we have a minus charge, so we have a 1 minus charge, so what are we going to do with that? So we're going to add an electron. So remember, electrons are negative, so if we have a more negative ion, we're going to have more electrons. So 7 plus 6 plus 1, that's going to be 14 valence electrons. So let's start to draw this out. So we have chlorine and we have oxygen. So we'll draw our bond, and now we have 12 valence electrons to work with. Remember, each bond is 2 electrons, so 14 minus 2 is going to be 12. So let's start to fill those in. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each one of these has its octet. 2, 4, 6, 8, 2, 4, 6, 8. And remember, since this is a polyatomic ion and it's negative, we'll have a negative charge for this ion. So helpful hints. So use the group numbers to tell you the number of valence electrons. Chemical formulas are usually written in the order that atoms are connected. So for example, HCN. So the central atom, carbon, is going to be connected to hydrogen and nitrogen on the sides. 3. In polyatomic molecules and ions, the central atom is going to be written first. So for example, CO2 The C is going to be the central atom, and the oxygens are going to be connected around it. So here we have COO3, so carbon, and 1, 2, 3. And this 2 negative charge, that applies to this whole ion. This whole ion is going to be a 2 minus charge. So SF4, so sulfur tetrafluoride. So we're going to have sulfur in the center, and then it's going to be surrounded by 1, 2, 3, 4 fluorine atoms. Resonance structures. So resonance is going to be a condition that occurs when more than one valid Lewis structure can be written for a molecule or an ion. Resonance structures, they're only going to differ in the position of the electron pairs. So the atom positions are never going to change. It's only the lone pairs or the bonding pairs that are going to differ. So for example, we have NO3 here. So we have 3 equivalent structures. So this N, nitrogen, is going to be in the center, and it's going to be surrounded by these 3 oxygens. So notice how in each resonance structure they have the same structure. The only difference is that the lone pairs and the bonds are in different positions. So here the double bond is here, and here the double bond is up here, and then this one, the double bond is over here. This oxygen has 3, this one has 2, this one has 3. Over here, this one has 2, 3, 3, 3, 3, and 2 over here. It might be easier to watch an animation, so here's trioxygen, also known as ozone. So remember our steps. We're going to draw out our atoms. Now let's connect them with bonds. Now remember, each one of these lines means 2 electrons. So that means we have 1, 2, 3, and 4 electrons. So now we can start filling in the rest of the 18 electrons. Remember, oxygen has 6 valence electrons, so 6 electrons times 3 oxygens equals 18. Alright, so let's just double check that we have all of our electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now let's look at each individual atom to see if they all have their octets. So we can start off with the central atom. So that has 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is happy. What about this oxygen on the left? Here we have 1, 2, 3, 4, 5, 6, 7. So this is not an octet. What about the oxygen on the right? 1, 2, 3, 4, 5, 6, 7. So the 2 oxygens on the ends are both unhappy. They don't have their octets. So let's try to fix this by making some double bonds. So let's make a double bond on the left side. So we move these electrons, and then they create a double bond. So how many electrons do these oxygens have now? The one on the left has 1, 2, 3, 4, 5, 6, 7, 8. The central atom has 1, 2, 3, 4, 5, 6, 7, 8, 9. And the one on the right has 1, 2, 3, 4, 5, 6, 7. So the central atom has 9, and the one on the right has 7. So we can move one of the electrons over to the end. So the one on the right has an octet, the one on the center has an octet, and the one on the left also has an octet. So this is our first resonance structure of trioxygen. Now, remember, resonance structures mean that they can have more than one form. So instead of the double bond being on the left, it could also be on the right. Now remember, electrons are always moving, they're always moving back and forth, and these electrons are going to be ping-ponging back and forth between all 3 of these oxygens. And eventually we can get a double bond on the right-hand side. Now let's check to see if we have our octet now. So we have 2, 4, 6, 7. 2, 4, 6, 8, 2, 4, 6, 8, 9. So let's try to move this one electron over to the left. And now we have our second resonance structure for trioxygen. And this picture is showing you the same exact thing, except it's just not animated. So on the bottom we have our 2 resonance structures, and they're going to ping pong back and forth between these 2 variations of the same molecule. Half of the time it'll look like the one on the left, and half the time it'll look like the one on the right. So polyatomic ions can also exhibit resonance. So here's an example of NO3-. So the double bond can be up here, it can be over here, or it can be over here. For carbonate, The double bond can be over here, it can be up here, or it can be over here. These structures can ping-pong back and forth to one another. Exceptions to the octet rule. So far, whenever we talked about an atom or a molecule, we always talked about the octet rule and how atoms are most stable when they have 8 valence electrons. However, there are some molecules and ions that don't obey this octet rule. So there's 3 different categories of these exceptions. First, there can be an odd number of valence electrons. Second, there's less than an octet. Third, there's more than an octet. So if we have an odd number of valence electrons, we won't be able to form an octet because 8 is an even number. For example, we have NO2. Nitrogen has 5 valence electrons. 2 oxygens will have 12, so 12 plus 5, that'll get you 17. And since 17 is an odd number, we can't have an even number of electron pairs. So here we have 2, 4, 6, 8, 10, 12, 14, 16, 17. Less than an octet. So another exception to the octet rule are called sub-octets. Sub meaning less than, octet meaning 8. And this group is relatively rare. One example is BH3. B is called boron and it's a group 13 metalloid. So it'll have 3 valence electrons. So it can form 3 covalent bonds with other atoms. And in the case of BH3, it's only going to share 6 valence electrons. Coordinate covalent bond. A coordinate covalent bond is going to form when one atom is going to donate 2 of their electrons to another atom that needs 2 electrons. So for example, we have here BH3 and NH3. The nitrogen of NH3 is going to donate both of those electrons to form a coordinate covalent bond. More than an octet of valence electrons. So the third and largest group of compounds that don't follow this octet rule is called an expanded octet. This is also called hypervalency. So it has a central atom that's going to contain more than 8 valence electrons. So when you draw the Lewis structure for these, they'll have either extra lone pairs or more than 4 bonding atoms. So one example of an expanded octet is going to be PCl5. So as you can see in the center we have a phosphorus and it's surrounded by 1, 2, 3, 4, 5 chlorines. So 10 electrons are going to be shared for this single phosphorus in the center. So 2, 4, 6, 8, 10. So that's more than an octet. Another example is going to be SF6. So we have sulfur in the center and it's surrounded by 1, 2, 3, 4, 5, 6 fluorines and it's going to be sharing 12 electrons. So 2, 4, 6, 8, 10, 12. So for a summary, different models can be used to represent different molecules. Resonance occurs when more than one valid Lewis structure exists for the same molecule, and exceptions to the octet rule also occur in some molecules.